Good morning, everyone. Welcome to our webinar on optimizing blending processes with OptiBlend. I'm Vaishnavi, your moderator for today's session, and also the head of global marketing at Systech Solutions. We are excited to have you join us today for this session. Hopefully, it's insightful for all of you. And we will be exploring how data science and analytics are revolutionizing the manufacturing industry, specifically through blending optimization. And before we begin, I'd like to introduce our expert speakers. Joining us today is Professor Shankar Narasimhan, the MS Ananth Institute Chair Professor at IIT Madras and co-founder of GyanData. He's an expert in data mining, process design, and optimization. Professor Shankar has co-authored over 100 research papers and is a leading authority in his field. It's great to have you here, Professor. We also have with us Madhavan Sourirajan, Head of Business Solutions at Systech Solutions. Madhavan has extensive experience in data analytics and manufacturing sector, having implemented several business intelligence solutions for us. Excited to hear your expertise and insights on how data science and analytics can drive improvements in blending and overall operational efficiency. Looking forward, both of you. And before we start, I will cover a few housekeeping items. We've carved out some time for Q&A towards the end of the session. So type your questions into the Q&A box of your control panel, and we will get right to it after the presentation. Now I'd like to hand it over to Professor Shankar Narasimhan to delve deeper into the concept of blending in the manufacturing industry. All yours, Professor.
Thank you, Vaishnavi. I'm just going to share my screen. I hope everybody is able to see it.
Yes, Professor, we can see it.
Yeah. Good morning to all of the participants. My aim here is to give a very quick overview of the blending process, an important problem in many industries. And some of you may be aware of it, but it's always a good practice to go over some of the elements of this problem. And to just put it in context, I mean, most of us are familiar with the process of making dough for our bread in the house, right? Where we mix flour, maybe yeast and milk, and then in water with various proportions, and kind of knead the dough and then bake it in an oven, maybe setting it at the right temperature. After probably let it ferment for some time, right? And then we adjust the temperature and the time for baking, and we produce the dough of a certain quality we get. So the aim in all of this is to produce a product that doesn't crumble, maintains a certain amount of structure, as well as what you call has good taste and so on, right? So in general, the problem of blending in industry is also similar. You have a set of materials, raw materials, which we have shown in the left as raw material 1, 2, 3. They could represent the flour, the yeast, or the water, and so on. And in different industries, these raw materials represent different what I call streams. And then each raw material themselves actually have properties. For example, if you're talking about the flour, in this case, the grains particle size distribution could be one of the properties of the raw material, right? And similarly, each of the raw material comes with its own set of properties, which we call the property set 1, 2, or 3, right? And you want to mix these raw materials in different ratios. And then after mixing it, maybe if it's a batch process, you would like to mix it at a certain RPM, probably adjust the temperature if temperature is an operating variable. And after some time, take it out of the batch, right? That you get the desired product, right? Or if it's a continuous process, you might actually blend it and continuously withdraw the product. In both these cases, whether the operation is continuous or a batch, you would like to produce a product of desired properties. And these properties themselves could be a variety of them. It could be, for example, in the case of powders, it could be the stability, the flowability of the powder, or it could be the solubility of the powder in different solvents. Or it could be, if in the case of liquids, it could be the viscosity of it and the stability of it, and so on and so forth. So the raw materials and product could either be liquids or solids. In every case, you want products of desired characteristics or desired properties. That's what we call the blending problem. And this problem, although it's very simple, has cuts across a wide variety of industries. You will find this problem. For example, starting with the bottom left, if you look at the iron and steel making or metals processing industry, you're blending different kinds of ores, sinter, pellet, for example, in the case of iron and steel, to produce the iron, right? And if you're looking at a fertilizer plant, you're trying to actually produce a product having the appropriate nutrient profile by mixing different nitrogen sources or phosphorus sources and potassium sources and so on. Again, if you look at a refinery, for example, you might have different kinds of crudes that you have actually obtained from different sources and perhaps stored in different tanks, and you want to blend them so that you produce a crude which your unit operations such as distillation or reactor is capable of handling. If you look at again the beverage industry or even the cosmetic industry, you're actually blending different kinds of flavors or coloring matter and so on, preservatives, in order to produce a product. And we can just go on again in the paint industry, again, color, viscosity, all of the stability. These are interesting properties that product properties you want to control by mixing different raw materials, pigments, and so on, resins, and so on. Lubricants is a very common problem, blending problem, where you're taking base stocks and actually adding several chemical additives so that the lubricant has certain characteristics in terms of when you use it in either in a engine. For example, it's score properties, it's flash properties, and so on and so forth. Cement industry is another case where we have blending of raw materials, where your limestone, clay, gypsum, and you're trying to actually control the setting time as well as the compressive strength, example of the cement that you produce. Pharmaceutical is another area where you're mixing different APIs and excipients to produce powders that have certain flow characteristics, solubility characteristics, as well as its diffusion characteristics in the medium. So you find that these are not an exhaustive set of things, but there are common examples. You can see a wide range of industries where blending is actually used. And so, therefore, it's an important problem that you can actually, where you need to actually maintain strict quality control, and cost could be also an implication. Now, in order to view this as a generic mathematical problem, so there are three elements to it. I will start with the center one, which is the decision control variables. What you have in your hand is the ability to manipulate the blend proportions. So in some cases, you might actually be able to manipulate also the choice of raw materials. You may have different sources and you may want to pick one or the other. Or, for example, if you have stored the material in different tanks, you may want to choose one of a few tanks in order to actually blend the raw materials. And then you might also have control over some of the blending parameters like temperature or the time of mixing or the RPM of the agitator and so on. So these are the variables you have within your control. And you want to produce product of desired properties, which we call constraints. So you want these properties such as stability or viscosity to be within some range. And that's what we call as constraints. And you may also have some availability constraints. You may not have all the raw materials. You might only have a finite amount of raw material. And these are also imposed as constraints in the problem. So you have this ability to manipulate these decision variables to produce a product satisfying these constraints. But you want to do it in a way which is cost effective. So based on the cost of raw materials, you may want to actually minimize the total cost of the blend, right? That's your economic incentive for applying this blending optimization problem. And in some cases, you may want to actually look at objectives such as longer shelf life, which might actually be determined from the acidity and so on and so forth of the blend. So these are some of the objectives that you may want to actually, one or more objectives that you may want to satisfy in order to produce a product with of desired characteristics by manipulating these decision variables. In order to solve this problem, you basically have two requirements, what we call a blend model that tells you how the output properties change with respect to the proportions that you use as well as the raw material characteristics. This blend model is a very important or key component of this solution process. Once you have this model, we can embed it in an optimization strategy to find out the most optimal minimum cost blend or product that has a longer shelf life and so on. Right? So these are the two basic major elements of this thing that we have incorporated in the product. And in most cases, what happens is the model that relates the output properties to the input, essentially the ratios as well as the raw material characteristic, may actually be available with the organization. If they have been doing this for a long time, they may have some proprietary model in terms of equations and so on, which they can use. But in case that when they do not have such a proprietary model, one can use historical data to build what we call an AI model, a machine learning model, which with today's tools, this are possible, provided you have historical data, right, of this process. We can then build this model. And that's the first component of our product. There's an inbuilt mechanism for building an AI model from the historical data, operating data that you may have in the past. Once you have such a model, we can actually embed this in an optimization strategy. So essentially, we post this problem as internally as an optimization problem with the desired objective function, which you can define, and the constraints, what are the property ranges that you want to actually meet, availability, all of this you can actually post in a very English-like language, in a language that is familiar to the the company itself, operating company. Once you actually describe this problem, it takes this model that it has built, applies an optimization strategy. In this case, we are saying it's a gradient-free. This is just a solution strategy that has certain nice properties that doesn't require the function to be differentiable. And so it's a very good technique that solves the problem and produces what we call a blend, appropriate proportions that you should use in order to produce a product that satisfies your constraints as well as the cost is as minimal as possible. And that's something that you get as a solution of this problem, right? So what are some of the potential applications? I've just given a few, again, not exhaustive. Well, let's take the paint industry. You are looking at maybe color of the paint, the viscosity of the paint, the durability of the paint, and so on. And you're actually trying to minimize. In all cases, we have chosen cost as the minimization thing to illustrate, but you could change this objective to your desired type of thing that you want. So here again, if you look at the lube industry, we are talking about base oils and additives. You describe their raw materials that you have and the additive properties. You produce a lubricant with desired viscosity, thermal stability, and so on, flash point, core point, and so on. And you want to do it in such a way that the cost is as minimal as possible. If you look at the cement industry, again, you're looking at a variety of raw materials like limestone, gypsum, and so on. And you're again trying to minimize or maintain the compressive strength of the product, the setting time of the product, and so on. And trying to find the least cost solution to this problem. The pharma industry is another example that we have written here, where you are trying to combine APIs and excipients in order to actually produce drugs or powders with desired flow characteristics or dissolution characteristics and so on. And you again want to find a minimum cost because some of these APIs are fairly expensive, and therefore you want to make sure that you're not overusing them. So these are some typical examples that I've illustrated. There are a lot more. I think this product, I believe, has a wide applicability, and it allows you to describe in the language of your choice, essentially, and not in terms of a mathematical thing that people usually get turned off. So I will stop here and later on take questions regarding the thing and hand it over to Mr. Madhavan to talk about the product itself. Yeah.
Absolutely, absolutely. Thank you, Professor Shankar, for that detailed overview. And blending is indeed a critical process in manufacturing, and it affects it affects everything from product quality to operational efficiency. Thank you for sharing your insights. And yes, next Madhavan will highlight the key features of OptiBlend and how it can transform your blending processes. Over to you, Madhavan.
Yeah. Thank you, Vaishnavi. Is my screen visible?
Yeah.
Yeah.
Yes.
So in my session, I'd like to introduce our product OptiBlend and give an overview of some of the key features and the advantages that comes with the product. So what is OptiBlend? So this OptiBlend is a data-driven AI-based product which has been designed and developed to help us optimize blending processes across different manufacturing industries. So it uses a data-based modeling and optimization approach by leveraging historical data and machine learning techniques. So how does this OptiBlend product work? So the schematics of our product it has two parts to it. So the first one is the database modeling part, and next one is the optimization part. So coming to the modeling part of it, the process begins with gathering of historical blending data, which is inclusive of different raw material proportions, different raw material properties, and the corresponding output product characteristics that were achieved in our historical blending scenarios. So with that, a regression-based machine learning model is created and trained with the historical data that is available with us. In this training process, the model learns the different effects of the different proportions and the different properties of the raw materials on the output product characteristics. So once trained, the model can be used as a simulator to simulate different raw material blending scenarios and different blending proportion scenarios and predict the output product properties. So now coming to the next optimization part of the product. So first we define a configuration for the optimization process. So what do we define in this configuration? So we define our objective function or the objective which could be to minimize our cost or to optimize our quality, etc. Then we also define the process constraints if there are any. It could be like Professor highlighted, it could be availability of raw materials or blending proportion constraints itself. Then we also define the desired and expected product properties. So with this configuration in place, the ML performs the optimization process considering all this configuration element into consideration. And the output of the optimization process is a recommendation. So which gives us the optimal blend proportion that will meet our product requirements. So that's how OptiBlend works to help us optimize our blending processes. So now, coming to the advantages and the key features of the product. So OptiBlend is a versatile tool. By versatility, what we mean is that it can be used across different industries. It is not restricted to a specific type of blending process or a specific manufacturing industry. So this makes it a versatile tool that can be used across different industries, like highlighted by the professor. So it can be used in a drug formulation process for a pharma industry, or it can be used in a beverage production process in the food and beverage industry, like so on and so forth. So next is the accessibility of the product. So OptiBlend is available as a SaaS offering, which means that there are no installation requirements or any specific hardware requirements for our product. So it is basically ready to use from the word go. And next is there is no programming knowledge is required for the users, which means anybody who's involved in the blending process can use our product with ease. And from the data gathering to the ML model creation and training, the optimizer configuration. So all these elements of the product is available through a user-friendly GUI interface, which is very easy to use and very straightforward for all the users. So then coming to the comprehensiveness nature of our product, right? First, it offers an automated database modeling option where our product chooses the right regression technique and builds and creates an ML model out of it. On the other hand, if there are some users who have some modeling knowledge, it also allows them to integrate custom models or select specific regression techniques of their choice for their blending scenarios. So it also allows us to manage and maintain the models that has been created, which could be when there is a need for retraining or fine-tuning the model that was created previously. So in that way, it's a comprehensive tool which caters for all the different types of users. And coming to the benefits of the product, one of the tangible benefits of using OptiBlend is that with its optimization engine and process, it helps us to reduce the number of experiments or iterations needed to achieve an optimal blend proportion, which in turn reduces our turnaround time. So this helps us to optimize our process at a quicker pace, at reduced cost, and achieving the desired quality. So in a nutshell, OptiBlend is a user-friendly product which effectively addresses our blending process challenges. So it helps us to achieve the desired product characteristics efficiently in a cost-effective manner. So with that note, I'll wrap up my session, and thank you for your attention so far, and we'll hand over to Vaishnavi for the next section. Thank you.
Thank you so much, Madhavan, for your insights. And now we'll open the floor to questions. So please use the Q&A feature to submit your questions. And I see some of them there. So let's address some of the questions that you've sent in. Professor Shankar and Madhavan are here to provide the insights. Feel free to ask about the blending process, optimization techniques, or even the features of it. Okay. So we have the first question with someone asking, how does OptiBlend compare with other optimization tools like GAMS, IBM iLog, Gurobi, AMPL, etc.? Professor Shankar, I'm sending this question your way. How would you respond to that?
Yeah. Blending has been a very operation that has been actually practiced by several industries, and some of them may have used these tools for solving their problem. The big difference is these are tools that are actually developed with a mathematical perspective in mind. So they don't have the language that typically industry people use. So they are talking in terms of mathematical techniques, and therefore one needs to do two things. One, the language itself is different, so it becomes less transparent. Secondly, someone has to learn the language details. It is not a programming language. I do understand one can use programming languages also to do it. That will be much harder. These tools allow you to simplify the thing. Nevertheless, you need to actually still learn some language features in order to use these tools. Lastly, the great differentiator between OptiBlend and these tools is they don't have a modeling feature at all. The model is supposed to already be available with the user, and they have to describe them in the mathematical way. Whereas we in OptiBlend actually can develop this model from historical data, and that's the big differentiator I see.
Oh, great, great. I hope you got your answer that you're looking for, and sort of highlighting the value differentiator for OptiBlend. Okay, and we have the second question with someone asking, one, what are the data requirements for using OptiBlend effectively? And two, how should users prepare their data for optimal results? Professor Shankar, can you share some insights on this one?
So in any data-driven modeling exercise, I mean, typically historical data is a requirement. In this particular case, we are talking about anywhere between 2 to 3 months of data, past experience, where the data you need to actually prepare in an aligned fashion. What I mean by an aligned is you need to actually have different tried out, whether you have tried out these experiments in a lab setting or on the field. So you have blended different proportions in the past, and you have actually noted the resulting product properties. So those actually have to be available for developing what we call the model, because this is a supervised technique and you need them. So that's the requirement. On the other hand, if a company has proprietary correlations that they have developed in the past, then they can be directly input into the software. So it allows you both mechanisms, catering to legacy what I call knowledge, or new knowledge that you need to be actually inferred from data. Both possibilities are provided in the tool.
Sounds good. Sounds good. Hope that answered your question. And there's another question. How much customization is allowed in this product? If I already have a blend optimization approach, can I migrate it to OptiBlend? Madhavan, I'm sending this to your way. Please go ahead.
Yeah. So OptiBlend comes with customization capabilities inbuilt in the product, and it allows us to integrate custom models, and also allows customization in the different components that is available as part of the product. So probably once we have a walkthrough session of how the product works in our upcoming webinar, so probably looking at that, the user can see how much of customization is needed from the existing features for his particular blending scenario or for his particular industry. Then from there on, we can explore more on what customization needs that the product can address.
Okay, thanks for that, Madhavan. The next question that I have is Professor Shankar, I'm sending this one your way. We have a question from Anuj. In pharmaceuticals, we want to know when blending is complete instead of optimizing the material concoction for blending. We know right amount of material, but sampling leads to variation. Is there any solution to this?
So if you really want to know the what you call endpoint detection, as we call it in a process, to know whether the product has reached a certain quality specification, so one needs to have some kind of online measurement. I mean, this could be an online sensor, or you could actually take samples from this and come to the lab, which will take a little bit of delay. So it depends on how long it takes for the samples to be analyzed. And depending on that, that feedback mechanism has to be put in. Right now, OptiBlend is what I call developed as a product for prescriptive, right? If you need a control angle to it, one can add this other component to it so that you can have real-time or near real-time, what I call control of the product specs. But then there's feedback necessary for that. Yeah.
All right. Thank you, Professor. Let's get one more question in. And Professor, I think it's for you again. Madhavan, feel free to add on. How does OptiBlend integrate with existing systems and software?
Yep. So from an integration standpoint, right? So we would want to integrate it. We can integrate OptiBlend and gather data from existing systems. We have features via APIs to ingest data to OptiBlend, or we can also connect it to databases. Like that, we have connectors to different systems to fetch data from the historical data from that system and further use it for the optimization process.
So if I may add, I think it is now conceived as a SaaS product where people actually run it off the cloud. However, if one wants the component to be integrated with their existing SCADA system as part of their internal thing, that requires some additional effort from our side, but it can be done. In principle, can be done.
Thank you, Madhavan and Professor. Thank you, everyone. Feel free to add the questions and post the webinar session. We will be happy to answer them for you, even if we have not gotten them to you here. Right. Thank you, everyone, for attending the presentation today. And we'll be sharing the recording of today's live webinar along with the QA report with all of you. Thank you, Professor Shankar and Madhavan, for sharing your insights. And a big thank you to GyanData for joining us and co-presenting this webinar with us. We also invite you to join us for the second webinar, where we'll provide a live demonstration of OptiBlend in action. And this will be an excellent opportunity to see the tool's capabilities firsthand and understand how it can be integrated into your processes. Right, we see one question on how it can integrate with the existing systems, and while we briefly touched on it, next session will be more useful to you there. Right, so thank you all once again for your time, and we look forward to seeing you in the next session. And please don't hesitate to email us at info@systechusa.com. And thanks again for joining us. Before you go, please take a moment to fill out the survey, and see you all next week. Thank you so much. Thanks, everyone.